Today, we're going to get up close and personal with a robot that's not only been successful so far in the Decode season, but has also been wonderfully intentionally designed.
Synchronously asynchronous opens the gate to empty the classifier.
Empty the classifier.
I'm Coach Pratt, and I've been teaching robotics design for over a decade now, and I've led FTC teams to winning national championships. And today, I sat down with Team 2393 JFK Robotics, and we go over their whole strategy for the Decode season. We'll talk about some awesome compliance they've got on their little intake, a dual shooter method that allows for some manual indexing, and a whole bunch of little tidbits about intentional design that can really get your team thinking about how to make their robot better. Tell me about your approach to the season. What was your general strategy to the Decode season?
This season, we really wanted to emphasize the whole design with purpose, design to work first try or iterate till it works.
We had the full CAD already before we machined and actually made anything in real life. A big issue with last year's seasons was that we had our drivetrain made, so it was just the wheels, and we really had no clue what subsystems we were going to use. So by having everything designed out this season, it was really helpful to know what's going to line up. And with all the prototyping that we already did with 3D printing, it was really easy to just slap it on and it all worked and fit together really nicely.
Yeah, and then strategy-wise, we mostly wanted to be a big, heavy bot that could play defense and not break with hits. So that's why our bot looks so dinged up.
Let's talk on your intake first. How do you actually get your ball into the robot and onto these ramps?
We started out with 2 sets of rubber band wheels, but it didn't have enough grab. As you can see, we have 1 for the second stage, but the first stage on the rubber band wheels, it was terrible. And so the ball would stay here for about 5 seconds before actually going into the robot. And that was the main issue because in order to have the most efficient robot, we need to be able to touch a ball very lightly and instantly have full grab over it. So by using Go Build a Gecko wheels, we've had a lot of these laying around. We found that this was the most effective grippy way to grab them. And especially with our motor going at almost 1,000 RPM, it just sucks the balls right into our robot.
Yeah, and then we also had issues with finding the correct amount of compression from ball on the floor to intake. So we added suspension to our intake, so it has freedom to go up and down as high as it wants, but it has these rubber bands pulling it back down, so it really sticks onto these balls and pushes them into the ramp. And then these mechanism wheels in the center were because this fin here would sometimes have the ball stuck on a hole. So the mechanism wheels divert it to one of the ramps so that it can't even go there. And then the second stage is the rubber band from the first test, which worked very well because it was more delicate and less rough. It really just lightly pushed it into these balls without pushing it into the shooter early. And it moved it quickly once on the ramp with the right compression.
So it sounds like you've tried to use, with that rubber band wheel, you tried that with compliant wheels as well, but it was forcing it too fast into your actual intake shooter before you're able to get that out.
Yeah. The rubber band intake, we've definitely seen it work, but it's just finding the right compression, the right number of rubber bands, the rigidity of the rubber bands, how big the sprocket is it's on, that really we didn't see worth testing when we could plan better an intake that had a consistent amount of compression and better grip all in one.
Did you have to do much testing in deciding how much compression you wanted on that intake as it lifts up and down onto that ball?
One of the things we did was when we were designing the arm, it was able to slide up and down here. And since this is nonlinear and this is nonlinear, it gives us about like a 1-inch jump on how high up and down it can go based off the standoff. So it could go further down or higher up based on what we want. And the rubber band, we tested many different strengths of that and found that it didn't really need to be that strong to fully push it into the second stage. So with the use of the rubber bands and the modular here, we could kind of test on the fly.
I love having slots inside of your design. So it allows you to have some extra compliance design. Love that. Great prototyping as well as, just realistically having something that's final, because now you don't have to reprint these lever arms every single time, right? You see these little things lots of teams don't think of, but it makes your design so much simpler. Okay, so it comes in through this intake. You have these 2 little vector wheels that are able to push it out of this little fin you're saying in the middle. And it almost looks a bit like you've got this, I feel like a little kid going down a water tube slide. I feel like I need a tube to put on these inner tubes. So we get it up, we push it through there, and then where are we going from there?
One thing I actually really like about our intake and transfer mechanism is the mechanism wheels, which helps us get through our entire robot very quickly and efficiently. upon first look, you might think, oh, well, why are your mechanisms diverting the balls? Most teams want to converge the balls into one track. But however, because we had that jamming issue like Ryan was talking about, by separating them into 2 tracks with these mechanism wheels, we can essentially get twice the throughput. And the transfer mechanism is very efficient with these gecko wheels, yet again, being used up here with servos, which transfer the ball from the transfer and the ramp into the actual shooter.
The wheel with more compression than the first stage. This is so that it can act as a hard stop. So we can intake as much as we want and keep intaking and hold these balls in place, but they won't go anywhere past this or into the shooter. This hard stop, it can then be activated independently using servos on sprockets mounted integrated into our shooter. And this comes from our design with intention. We could have had these servos, offset, but we decided we wanted to be compact and protect them.
Yeah, I think that's another nice little thing too. You say you've got servos set up on sprockets. There's a bit of a focus in some FTC teams of needing timing belts for literally everything. But having some plastic chain is a really useful prototyping tool, as well as just a functional finished prototype. I mean, it's good enough for motorcycles to go, 600 kilometers an hour. Chain is likely good enough to send a flywheel at 1,000 RPM. And it makes it so much easier to do that design. You don't have to have things totally set. And I like that this is what you're talking about, where you have that soft rubber band wheel, push them into something that's a lot harder compression. That little gate mechanism almost with those little servo wheels. That's an excellent little way of being able to feed that in. Do you have any sort of color sensing at this point in time to decide where you have balls going into respective shooters?
We do have a color sensor. It was integrated into our drivetrain plates, very easy to take on or off. And we did not have time to code it. We did not give the coders really enough time for teleop, and we favored auto because we figured that's what would separate us, is being able to consistently take the front auto, take the 6 to 9 balls, and not be the one in the back that's just shooting 3. We were very close to integrating into Tele, having a shoot motif automatically. It just never got finalized to a point where it was faster than just shooting automatically with coach's advice or just off vision from yourself.
Let's talk about your Outtake. How are your flywheels running there?
So our flywheels are Andy Mark compliant wheels. The blue ones, I don't know what durometer they are, but they're both connected through a very long D shaft, as you can see this through. So when one spins, they both spin, essentially making one larger flywheel. And that helped us with keeping our RPMs up between balls. So we use 6,000 RPM motors with, I believe it's 1-to-1 gear ratio, 21 teeth that we printed in PETG for our pulleys, which we found that 3D printing parts like our gears and pulleys has actually been really sustainable because they're very fast to print, and like us with generators that are on shape and Fusion 360, it's really easy to drop exactly what you need. One of the issues we had at the start of the season, if you want to come around to the back, Ryan, with our motors, as you can see, the motors are technically facing opposite directions. So at the beginning of the season, we actually had an issue. When we turned on the motors, they would just go in opposite directions and the whole thing would jam. One motor was trying to spin this way and the other motor was trying to spin this way. So we had to swap our code, and the programmers had a lot of fun trying to troubleshoot what was going wrong.
We also keep our shooter spinning up for the whole match at I think around 1K, 1.5K, somewhere in that range, just so that we spend less time shooting up when we actually lock onto the Limelight, and so that we, after shooting, can spin up again faster.
You use the 4 compliant wheels as a way of adding extra weight to your flywheel so that you get more momentum or more inertia on that as well. I think that's something I'm not sure a lot of teams have considered, the fact that just adding more wheels and adding 2 of them definitely adds in that extra inertia.
Right. We experimented with adding a flywheel in addition to the wheels that are already on here. So we designed and custom printed inserts that would go into each of these little slots right here. But we realized very quickly that it changed the compression and all of our tuning data was out the door. And so we decided, okay, let's rewind one step and go back to where we had no inserts and go back to where tuning data was actually correct with what was actually on the robot.
And in your shooter, is it the same compression all the way around, or do you reduce compression as you get closer to the edge?
It's not the same compression all the way around. We tested many different hoods with different angles and compression levels, and we just found this one was very consistent, close, and could also shoot back. Yeah.
So the path that the ball takes, to see if I can get a good view here, you can see right at the bottom, there's almost no compression on the ball. And this is where it's still in contact with the flywheel. And that's how our transfer works. Once it gets past this transfer, it's in contact with the flywheel for what's that? Almost like 140 degrees. And so that's something we're actually going to adjust for our next robot, because the longer we're in contact with the flywheel, then the more it slows down. And so we've decided that instead of having the ball be in contact with the wheel for so much going around this arc, we're going to try and feed it up directly from the bottom. And that way, as you can see, there's a lot of compression right here compared to where we were before. And then as it exits, it gets less compression till there's obviously nothing.
Now, question for you on the Limelight. Now, obviously your turret, well, it's not a turret, it's a fixed shooter and the whole robot shifts. How have you managed, or how have you found that as a strategy with the entire robot shifting to be able to line yourself up on a tag?
As we mentioned before, our bot is really heavy and we use a lot of standoffs. And of course, with parallel plate design, everything is super rigid. I mean, this thing could probably take a fall from, maybe not the height of the building, but it could take a fall off the cart and it will be fine. So we use that to our advantage by being able to play heavy, heavy defense. It got really loud on the fields, crashing into other bots, blocking them right as they were about to shoot. But it has definitely been an issue with, if we get knocked while we're shooting, then there's nothing we can really do. We just hope that our Limelight camera aligns well enough.
Another question for you. Do you have any sort of automations that help your drivers make your life a little bit easier? Do you have any sort of lights on here? Do you vibrate the controller when certain things happen? Tell it to know the flywheels are up to speed? Anything along those kind of lines?
Yeah, so there's one button which will find the right speed and line up the robot with the fiducial ID. And then when the RPM's all the way up to speed, it vibrates, I'm pretty sure. And that's when they know to shoot manually. And they shoot manually so that we can try to get that motif point by having two independent shooters. So we can shoot left if it's purple, if you need purple, right if it's green, if we need green. It all depends on the situations. There's many, depending on the intakes and the motif.
Do you have any sort of basing or any sort of plans for trying to fit two robots in one base at the moment?
We're planning on using the every bot park with just that tiny little kickstand. I've seen a lot of teams use that. I think that's definitely going to be the best way. I think linear slides, being able to push all the way up 18 inches is a little bit too risky. If something breaks and there's a possibility of completely destroying another robot. And I don't want that that responsibility on us. So I think a lot of teams, if everyone just uses the kickstand method, it's a lot safer, it's quick, and then all teams can do it. They can easily get a full park.
Mm-hmm. Yeah, maybe we can get a little more teams on board doing a kickstand method then.
Yeah.
Last question for you. What are you most proud of about your robot?
Most proud of? For me, it's definitely comes down to its uniqueness. We saw one at the second comp, but it was nowhere near as completed or finalized in ours. It seemed not as finalized. We've seen it in FRC once. I think they did it as a joke though. And then the other things that I'm pretty proud of is the powder coating aspect. We've had a lot of issues with electrostatic discharge and disconnecting. So we decided to powder coat a robot, add a layer of insulation, and use grounding strips because we couldn't disconnect. That's just, you can't lose a game off disconnect, especially if we're trying to win comps, go to regionals, win Inspire. You can't be disconnecting. The last thing that was big to me was we learned that the internal resistance of the battery is hugely important. A low IR, 101, somewhere around there, plus or minus 5, can make your robot 10 times more consistent.
I think one thing I'm most proud of is because we are very lucky to have a full CNC machine shop in our facility. So I'm very proud that I didn't make these, but one of the other members on our team made these number plates. And I just think they're really unique, and they were made within
1 day,
2 days, maybe.
I think it was.
So I really like how the team being able to see something. We didn't even have a plan for nameplates. And so the members of our team, I think it was Katrina, Rachel, they made this and they just whipped it up in a day, and they were able to get on that because they knew that needed to be fixed. And that's what I really like about our team. And I'm proud of most. We come together and we just see a problem and we fix it.
Thanks so much for taking your time to be able to share off your robot, talk about your designs. It's super cool seeing this thing up and running, and best of luck out there at regionals this season.
Thank you so much.
Thank you. Yeah.
All right. Really nice to meet you.